Alright everybody, we're back, and this video is going to be information related to section 16 of Unit 1 of AP Calculus. We've finally reached the end of Unit 1. A whole lot of videos and lessons in Unit 1. This is working with, like I said, section 16, which is working with the Intermediate Value Theorem. We're going to start by introducing two continuity-based theorems, and then look at a few little examples utilizing those. Hopefully I can get it all done in one video, but we'll see. Alright, and I call these continuity theorems because both of them that we're looking at here on the front page rely on functions being continuous. We're going to look at the Extreme Value Theorem for continuous functions and the Intermediate Value Theorem for continuous functions. You want to make sure you keep these two straight and what they are. They're commonly kind of paired together because they both rely on continuity in their hypothesis, but different conclusions that we can make based off of a function being continuous. So let's take a look at the Extreme Value Theorem first. It says, if f is continuous at every point of a closed interval a to b, then f takes on both an absolute maximum value and an absolute minimum value somewhere in that interval. Furthermore, for some x sub 1 and x sub 2 in the closed interval from a to b, we have that f of x sub 1 is equal to our minimum, and f of x sub 2 is equal to our maximum. Imagine for a second we have this function f of x that's continuous, and I'll just draw an arbitrary continuous function. Here we go. There it is, arbitrary continuous function on the closed interval from a to b. The Extreme Value Theorem guarantees that we have a maximum. You can see that maximum value right here. Guarantees that we have a minimum. You can see that minimum value right here. And further, that there's some x sub 1 value where f of x sub 1 is the minimum, and some x sub 2 value where f of x sub 2 is the maximum. We could actually have multiple x sub 1s or x sub 2s that take on the minimum or maximum value. It's possible for a function to hit its maximum more than once, or its minimum more than once. And furthermore, the function is in between those two values for every value of x. Okay? That's the Extreme Value Theorem. Now, if f of x is not continuous, those guarantees go away. Can I have a function that's not continuous on a closed interval that has a maximum value and a minimum value on that interval? Absolutely. It's absolutely possible. But I can also have a function that looks like this one. Where this function does not have a maximum value or a minimum value on the closed interval from a to b. Okay? Like I said, it's possible for a function that's not continuous to have a max or a min or both. Might have one, might have both, might have neither. But when the function's not continuous, all bets are off. When the function is continuous, we're guaranteed a maximum and a minimum. And that's the Extreme Value Theorem. On to the Intermediate Value Theorem for continuous functions. If f is a continuous function on the closed interval from a to b, and d is a number between f of a and f of b, then there is at least one number c between a and b such that f of c equals d. So again, I'm going to go back to my generic continuous function here. In fact, I'm going to use pretty similar to my same initial continuous function. There we go. Okay. Now, if I pick any number d that's in between f of a, okay, so there's f of a, and f of b. If I pick any value of d in between those two, so let's pick d right here, we're guaranteed that there has to be some value c that attains that value of d. Okay? And f of c is equal to d. Okay? So there's one number, at least one number c in between a and b. Notice c is in between a and b, where f of c is equal to that value d that we said was in between f of a and f of b. Mainly what the intermediate value theorem tells us is, if you know the function value at two endpoints of an interval, that function, if it's continuous, has to touch every possible function value in between those two endpoints, somewhere in that closed interval. Now, let's talk about when it's not continuous. Then again, all bets are off. Okay, so here I'll draw a function that's not continuous. Okay, here's the value of f of a. Here's the value of f of b. And if I pick a value d in between f of a and f of b, suppose I pick this value of d right here, you see that there's no place on the function where f of c is equal to d. Okay? There could be, but when the function's not continuous, it isn't guaranteed. We already kind of talked about that concept with the intermediate value theorem. If it's not continuous, there's no guarantee. Could it meet the conclusion of the theorem? Yes, but no guarantees. Only if the function is continuous on the closed interval are we guaranteed the conclusions of the extreme value theorem and the intermediate value theorem. All right, let's go over to the next page. Example 1. Let g be the function defined by g of x equals x cubed plus x squared minus 2x plus 3. Can the intermediate value theorem be applied to guarantee a value in the interval from 2 to 6, where g of x equals 35? So first of all, g of x is continuous. On all real numbers, because it's a polynomial. So it is continuous on 2, 6. Okay. G of 2 is equal to 2 cubed minus 2 squared minus 2 times 2 plus 3, which is equal to, that's a plus, which is equal to 11. And g of 6 is equal to 6 cubed plus 6 squared minus 2 times 6 plus 3. So that's equal to 243. Okay. Now, g of 2 is equal to 11, which is less than or equal to 35, which is less than or equal to 243, which is g of 6. So, since 35 is between g of 2 and g of 6, the intermediate value theorem guarantees a value where f of x, or no, g of x, where g of x equals 35. All right, because the function is continuous, and because 35 is between the function value at the two endpoints of the closed interval, we're guaranteed that that value must be a value of the function somewhere in that interval. All right. Example 2, we've got a table here. Selected values f of a continuous function are given in the table above. What's the fewest number of zeros of f in the interval from 20 to 30? Now, I can use the intermediate value theorem to help me with this. On the interval from 20 to 22, the function values at the endpoints are 2 and 1. So I know this function's continuous. That means I'm guaranteed to hit every value from 1 to 2 in that interval. So I'm not guaranteed a 0 in that interval. In the next interval, from 22 to 24, I am guaranteed to hit a 0 because 0 is in between the function values at the endpoints. So there's 1 on the interval from 22 to 24. I'm not guaranteed 1 from 24 to 26. Not guaranteed 1 from 26 to 28. I am guaranteed 1 from 28 to 30. So I'm guaranteed 2 because the function changes sign on those intervals. And since it changes sign, I'm guaranteed a 0 by the intermediate value theorem because 0 is in between a positive number and a negative number, no matter what those numbers are. All right, and example 3. Values of the function k of x are given in the table above. Which of the following is enough alone to guarantee a c in the interval from 4 to 9 such that k of c equals 4? Okay, so first off, k is continuous on 5 to 6. If I know that k is continuous on 5 to 6, by the intermediate value theorem, this function must take on all values in between the function values at the endpoints 5 and 1. 4 is in between 5 and 1, so this is true. Okay, let's do the same thing with the interval k is continuous on 4 and 5. Again, that guarantees that I've got a value between 2 and 5. Every value between 2 and 5. 4 is between 2 and 5. So that's true. And then part I, k is defined for every value on 4 to 9. Well, if we don't have the continuity, we don't have the guarantee that a value of c in that interval takes on a value of 4. You know, the function, while it could be defined, it could be discontinuous in a variety of places, and, you know, if it were discontinuous, it is possible that there is no value of the function that takes on a value of 4. So that means that only choices I and II are true. All right, folks, that's the end of this video. For those of you who have me in class, there are some practice problems for you to do. And a couple of my AP assignments, which we talked about in class. If you need information on the due date for any of them, let me know. And there you go. That's the end of Unit 1. Hope you enjoyed the journey with me, and hope you come back to carry on with Unit 2. Have a great rest of your day. See ya.